Hey everyone, welcome back. In this video, we're going to talk about how to graph the function or equation y equals log base 2 of x. The key to helping us graph y equals log base 2 of x is remembering that all a logarithm is the inverse of an exponential function. And then if we think about the graphical relationship between a function and its inverse, it's just a reflection over that line y equals x. So just to put that in writing, if we want to graph y equals log base 2 of x, the information that's going to help us do that is that it is the inverse of the equation y equals 2 to the x. Although if we wrote that equation in its exponential form, it'd look like x is equal 2 to the y, but ignoring that, it's the inverse of y equals 2 to the x, and therefore just a reflection of y equals 2 to the x over that line y equals x. All right, so now we just have to remember, what does the graph of y equals 2 to the x look like? Well, it's one of those increasing exponential functions, so its graph is going to look something like this. So in green, we have the graph of y equals 2 to the power of x. And remember, if we were to plug in x equals 0 to find the y-intercept of this function, we get the point 0, 1. If we plugged in x equals 1 into our function, we get y equals 2. If we plugged in x equals 2, we get y equals 4. If we plugged in x equals negative 1, well, we get 2 to the negative 1, which is the same as 1/2. Another thing to remember about our exponential function is that it has a horizontal asymptote as part of its end behavior, at least for its left end, right? If we head off towards x equals negative infinity, then the output of y equals 2 to the x is going to approach or get closer and closer to 0. All right, so now we want to use the graph of y equals 2 to the x to help us find the graph of y equals log base 2 of x. And here we have to remember and start using that inverse relationship between these functions. Remember, if we want to graph the inverse of a function, we just have to reflect that graph over the line y equals x. And so if we reflect our green graph representing y equals 2 to the x over the line y equals x, we will obtain the graph of our logarithmic function, the logarithm of base 2. And another thing to remember that can help us in reflecting the graph over the line y equals x is that if we have a point like negative 1, 1/2 on the graph of the original function, the corresponding point on the graph of the inverse function is just going to have those coordinates switched. So we'll have the point 1/2, negative 1 on the inverse graph. We'll have the point 1, 0 on the inverse graph, the point 2, 1, and 4, 2 on the inverse graph as well. All right, so if we take those 4 points on the original function and switch their x and y coordinates around, we generate these 4 points on the inverse function. I've gone ahead and plotted those. The other thing that will be useful to talk about and work with is that horizontal asymptote. So that is described by the equation y equals 0. Remember, the relationship between functions and features of a graph and the inverse graph, or the function and the inverse function, is that we reflect everything over the line y equals x, or switch the roles of x and y. If we reflect our horizontal line over the line y equals x, it turns into a vertical line. That vertical line is the vertical asymptote for our logarithmic function. So the horizontal asymptote as a piece of our exponential function becomes a vertical asymptote on the inverse or on the logarithmic function. And so that means as we get closer and closer to x equals 0 from the right-hand side, the output of our logarithmic function is going to have to be negative, and approach our vertical asymptote is going to have to go towards negative infinity. And that makes sense for a bunch of different reasons, right? X can never be negative, so we have to have something like a vertical asymptote here to stop us from hitting x equals 0 or going past x equals 0 to the left. And also remember, what is the input of a logarithm? It's the output of an exponential function. An exponential function can never output 0 or anything less than 0, so the inputs of our logarithms can never be anything equal to 0 or smaller than 0. And so now, if we just connect the rest of these dots, or try to connect the rest of these dots, and keep the same kind of curvature that our exponential had, but just reflected over the line y equals x, in pink, we now have the graph of y equals log base 2 of x. And so notice we started with an increasing exponential function in this example, and by finding the inverse, we found this increasing logarithmic function. We also have decreasing exponential functions, and that's going to be another example I think you should look at on your own. See what happens if we reflect a decreasing exponential function like y equals 1/2 to the power of x across the line y equals x, or equivalently, find the graph of log base 1/2 of x. You're not going to get an increasing logarithmic function. Instead, you'll get a decreasing logarithmic function. And so the graph of this single logarithmic function is going to have a lot of those important characteristics that the graph of a general logarithmic function is going to share. And so now that we've seen the graph of our first logarithmic function, we can go ahead and write down some of those basic log properties, some of these basic properties that we've written down for graphs of our other functions or for our other functions. And so these basic properties are going to be for a kind of general logarithmic function of base b, where b is just a positive number not equal to 1. So it could be a base 2 over here, or it could be some other number. And so the first thing we want to talk about is what is the domain of a logarithm. And what we can see from the domain of this graph, or just thinking conceptually about the logarithm as the inverse of the exponential function, that the domain is all x values greater than 0, or the open interval from 0 to positive infinity. Right, another way to get that result is just remember the domain of an inverse function is the range of the original function. And what is the range of an exponential function? Well, it's all numbers strictly greater than 0. So that must be the domain of the inverse or the logarithmic function. So after domain, the next thing we talk about is the range. And so the range of our logarithmic function, it doesn't matter what the base is. As we can see, we can get any y value we want from the graph of our logarithmic function. So that range is going to be all real numbers, or the open interval from negative infinity to positive infinity. And yet another way to get that result is just remembering that inverse relationship between logarithms and exponentials. The range of the inverse is the domain of the original function. The original function is our exponential function. What x values can we plug into an exponential function, or what is the domain of an exponential function? Well, we can plug in any x value. The domain is all real numbers. Therefore, the range of the inverse is going to be the same as that domain. It is also going to be all real numbers. Another couple useful properties of these general logarithmic functions, and this is helpful usually for like graphing a logarithmic function, are there's always kind of 2 points that we know our logarithms are going to go through, and that's represented by these 2 equations here. We always have that log base b of b is equal to 1, and log base b of 1 is equal to 0. We can see that from the graph over here. Just swap out b with the base of 2 and we'll get that. But we can also get this conceptually just by remembering what is a logarithm. A logarithm is the inverse of an exponential function, or what comes out of a logarithm is an exponent. It's the exponent that we have to raise the base to get the number inside. So if we wanted to even think about converting these logarithmic equations to their exponential form, that's saying the exact same thing. And yet another way to make sense of these equations. So what comes out of a logarithm, or if we're switching to forms, what comes out of a logarithm is an exponent. It's the exponent we have to raise the base to get the number inside. Well, b to the power of 1 gives us b, so that makes sense. What power do we have to raise b to get 1? Well, anything to the power of 0 is equal to 1. So what comes out of this logarithm has to be 0, because b to the power of 0 is equal to 1. And so our last basic property that I'm going to write down here is actually the one that we are probably going to use the most often, and that's the compositional relationship between a function and its inverse. They essentially undo each other. It may not always look like this, but this is technically the property we're always going to be using when we're solving these equations. And so these last 2 equations are just composing a function with its inverse. They always undo each other. So we can have that as the inverse composed with the function, or the function composed with the inverse. They both kind of undo each other, and you're left with that input, in this case x. So log base b of b to the power of x is going to be equal to x, and b to the power of log base b of x is also going to be equal to x. Right, if we kind of cover up the right-hand side for this first equation, we can make sense of it, because what comes out of a logarithm is an exponent. It's the exponent we have to raise the base to in order to get the number inside. So the number inside is b to the power of x. Our base is b. So the question we're trying to answer here to get the output of our logarithmic function, I just realized I'm covering this up, but I think you can still see it. But in order to get b to the power of x, we have to raise b to the power of x. So that makes sense. That's what we should get from this composition. And the same exact thing should happen over here. So what is the output of our logarithm? What does log base b of x actually give us? What is it equal to? It's equal to that special number that we have to raise the base of our logarithm to in order to get the number inside of the logarithm. So we're taking the base of our logarithm, raising it to that special number that gives us the number inside of our logarithm. So we better get that number inside of our logarithm when we do this. So the thing to remember here for this last property is if you compose a exponential with its logarithm, they're going to undo each other. You just got to make sure that the bases are matching up in order for that to happen.